We have shown here some notes we took in a previous video, and it shows myoglobin and hemoglobin oxygen saturation curves and how they're different. We've talked about these curves in two very important ways, and I want to make sure we summarize them carefully. I hope you have room to do this. If not, you can just put it on a little side sheet. When we look at curves, we have to interpret two different things about them. The first is the shape of the curve. And the shape of the curve can either be hyperbolic, let's just call that hyperbola, or it can be sigmoidal. Leave a little room in between so we can make a note there. Hyperbolic means non-cooperative. As we said before, that's shown here, where the slope starts steep and then gets more and more shallow until it flattens out. Sigmoidal, on the other hand, is cooperative binding. And we can see that with hemoglobin, where the slope is relatively shallow and then gets steeper again as binding gets easier, and then eventually it has to level out at 100%. So those are the shape differences, but there's another important one that we've talked about, and that is the shift. This is a totally different thing. Shift to the left as we see here for myoglobin. See how it's shifted way over to the left. That's a low P50, and what that means is tight binding. Therefore, shift to the right as we see here for hemoglobin is weak binding or weaker binding to oxygen. And it's worth noting that both of these things for hemoglobin, the shift to the right and the sigmoidal curve, conspire to give us what we need, which is this large gap between myoglobin and hemoglobin down in the low PO2 where the muscles are. Remember, the bigger the gap between the curves, the more efficient oxygen transfer is. That's what we want. Okay, so that's a bit of a review, but I want to now talk about this sigmoidal curve. We've talked about what it means, but here's a question. How does it come about? Think about it. What we really need is hemoglobin to be very tight binding, high saturation out here in the lungs, and weak binding and low saturation over here in the muscles where there's less oxygen. How do we do that? Well, actually, it's not really rocket science. Let's go on and talk about what's called the two-state concerted model of oxygen binding. If we need hemoglobin to bind oxygen tightly sometimes and weakly at other times, let's just simply have a hemoglobin that does this. It has two different states that are in equilibrium. Remember, hemoglobin is a tetramer. It has 4 subunits, and I'm showing those here in two different forms. One is a circle, the other is square, but these are just silly diagrams. It really looks like we've shown you in the real deal protein structure before. Now, these are just two slightly different shapes of hemoglobin. So this is hemoglobin in the tense state, or what we call the T state, and this is hemoglobin in the relaxed state, or R state. Now, these names don't really mean much. What's really extremely important is what the tense and the relaxed state mean with regard to oxygen binding. And here's the most important thing about this page. Tense state is set up so that it has weak oxygen binding. And the R state is slightly different, and oxygen just sticks to it better. So we have tight oxygen binding. Now, that is the basics of what we call the two-state concerted model of oxygen binding to hemoglobin. So here's how it works. As hemoglobin goes through the circulatory system, it's going to be in these two different states. The whole population can shift to the relaxed state. And when it does so, let's say it does so in the lungs, let's make a note of that. It binds oxygen very tightly, and oxygen, if it happens to be in the lungs, is going to hop on and stick very nicely. That's what we want. We want oxygen to get saturated in the lungs. Now, when we go and that hemoglobin moves out to the tissues, something about it changes and it switches to the tense state. Maybe part of the population or the whole population goes over here. And when the oxygen is bound to the tense state, it doesn't stick very tight, so it falls off. And this is what you want to be happening in the muscles and the tissues. So what we need to describe now going forward is, how does hemoglobin know to be in the relaxed state, tight oxygen binding in the lungs, but weak binding in the tense state in the muscles? It's because it works this way. Anything that binds and stabilizes the relaxed state makes it easier for oxygen to bind. And what's the most important thing that binds to the relaxed state? One oxygen binds, pushes the population to the R state, making it easier for more oxygen to bind. So if one oxygen jumps on, there are three sites left. If that pushes the whole thing over to the relaxed state more, that makes it to have more tight binding. And that makes one oxygen help other oxygens hop on. And every time a new oxygen hops on, it pushes more to the relaxed state and makes it easier for others to hop on. It's a really tough conceptual thing to understand, and we might just have to let that soak in and talk about it more in person in class, and we will do so. So let's leave it at that for now and move on to the next topic.